Hello students, in the last class we studied about the digestion and absorption of lipids. Today we will go into the metabolism of lipids. Under that we are going to see, so when you studied the chemistry of lipids, I am sure you have learned that they act as a source of energy. Now can you see these? One is the polar bear and the other one is the camel. Where do they get their energy from? Here. Now it is here where fat, which is the stored fat, comes into use and it is utilized as a source of energy. Isn't? Yes? Okay. So that's what we are going to study under lipid metabolism. First and foremost thing is we are going to see the oxidation of fatty acid, how fatty acids are synthesized, that is lipogenesis. Okay, that is under that synthesis of fatty acid, how it is elongated and desaturation of fatty acid, and how synthesis of triacyl glycerol takes place, and what is the role of adipose tissue in lipid metabolism. So what is ketogenesis, what is ketolysis, and what is ketose. Then we are going to study briefly about phospholipids and glycolipids. Plasma lipoprotein you have already studied, so we'll brush that once again. What is fatty liver and lipotropic factor. Then we are going to study about cholesterol metabolism and something about essential fatty acids and glycosides. Okay. Now what is atherosclerosis and the risk of factors for atherosclerosis. Now coming to the first topic, very important students, how you get energy by oxidation of fatty acid. So you saw the end product of fatty acid digestion and absorption. Digestion is fatty acid. Now how does it give energy? That is by oxidation. And the most important one is beta oxidation. Now what is this? Where does this beta oxidation take place? It takes place in most of the tissues. Remember, in most of the tissues you see beta oxidation, except for the RBC, because beta oxidation takes place partly in the mitochondria and RBC do not contain mitochondria, and also the brain. Okay, so most of the tissues show beta oxidation. Now more than 50% of the energy obtained by fatty acid oxidation is in the liver and muscle. Okay, where exactly in the subcellular site? It takes place in the mitochondria. Beta oxidation proper takes place in the mitochondria. What are the sources of fatty acid? One is those taken up from the plasma, that is the acid. Free fat originate mainly from the breakdown of fat in the adipose tissue. Second one is from chylomicron. Third one is from very low lipoprotein. Now what is the first step in fatty acid oxidation? Remember, the fatty acid is present in the cytosol, but the beta oxidation proper takes place in the mitochondria. Now the first and foremost thing, now this beta oxidation involves three steps. One is activation of fatty acid. Second step is transport of fatty acid from the cytosol into the mitochondria, and the third step is beta oxidation proper. Now let us see how activation of fatty acids take place. Now this, you know, a fatty acid has a hydrocarbon chain having at least one carboxylic group. Okay, remember this is the first carbon atom. The carbon atom of carboxylic group is the first carbon atom, and you count it that way, second, third, etc. So the carbon atom to the next to the carboxyl carbon atom is called as the alpha carbon atom. Next you have beta carbon atom, and the last carbon atom in the chain is called as omega carbon atom. Here oxidation takes place at the beta carbon atom, so that type of oxidation is called as beta oxidation. So now you just see here, so fatty acid gets activated. Now here, this fatty acid in the presence of coenzyme A using ATP gets activated into fatty acyl-CoA, or you can just say acyl-CoA. Now since it is using ATP as a source of energy, the enzyme is synthetase. What synthetase? What is synthesized? Acyl-CoA. So it is acyl-CoA synthetase. Okay, otherwise called as thiokinase. So in mitochondria, this thiokinase is present in the outer membrane of the mitochondria. Mitochondria has two membranes, outer membrane and inner membrane. So during this process, ATP is converted to AMP, meaning to say it has used up 2 ATPs. So this is the first step which takes place in the cytosol. Fatty acid is converted to the active form, that is called as acyl-CoA, in the presence of which enzyme? Acyl-CoA synthetase. Where is this present? In the outer membrane of the mitochondria using ATP. How many ATPs are used? 2 ATPs are used, because ATP is converted to ADP, ADP to AMP, giving out pyrophosphate. Is this clear? This is the first step in beta oxidation. Now, next, once the fatty acid is activated as acyl-CoA, which is present now here, which is present in the outer membrane. I said you have the mitochondrial membrane has two membranes, outer membrane and the inner membrane, and between the outer and the inner membrane of the mitochondria, you have what is called as intermembranous space. Is that clear? I repeat once again, you have the cytosol, you have the mitochondrial matrix. I said the mitochondria has two membranes, that is outer membrane and the inner membrane. The outer in between the outer membrane and the inner membrane, you have what is called as mitochondria intermembranous space. Is that clear? Now where did I say this enzyme is present? That is acyl-CoA synthetase. It is present in the outer membrane. Yes. So fatty acid in the presence of which enzyme? Acyl-CoA synthetase is activated as acyl-CoA. Remember students, this acyl-CoA is not permeable through the mitochondrial membrane. So this acyl-CoA combines with, so this forms acyl-CoA. Is that clear? That's the first step. Now this acyl-CoA now combines with a component called as carnitine, which is present in the intermembranous space. In between the outer membrane and the inner membrane, you have what is called as carnitine. It acts as a transporter. Now it combines with acyl-CoA in the presence of an enzyme called as CAT1, that is called as carnitine acyl-CoA transferase 1, and it forms what is called as acyl-carnitine. So it forms acyl-carnitine. Once acyl-carnitine is formed, it can move through the inner mitochondrial membrane. It can move into the inner mitochondrial membrane, and this is translocated into the mitochondrial matrix by an enzyme called as translocase, or to be specific, called as acyl-carnitine translocase, or you can just remember it as translocase. Is that clear? So this acyl-carnitine, now once the acyl group has reached the matrix, it will dissociate from acyl-carnitine, giving what is called as acyl-carnitine will dissociate into what? Acyl-CoA, and carnitine will be given out, and this takes place in the presence of another enzyme called as CAT2, that is carnitine acyl-CoA transferase 2, which is present in the inner membrane of the mitochondria. CAT1 was present in the outer membrane, and CAT2 is present in the inner membrane. So once carnitine is freed, that is translocated into the intermembranous space by which enzyme? That is translocase. Where is that present? That is present in the inner membrane. Once again we will memorize what we have studied. The first step in beta oxidation is activation of fatty acid. Where does it take place? It takes place in the cytosol. In the presence of which enzyme? Acyl-CoA synthetase. Where is this acyl-CoA synthetase present? In the outer membrane of the mitochondria. Mitochondria has two membranes, outer membrane and inner membrane, and between this inner and outer membrane there is a space called as intermembranous space. So this acyl-CoA synthetase is present in the outer membrane. This, in the presence of coenzyme A, gets converted, the fatty acid in the presence of CoA and acyl-CoA synthetase being the enzyme, gets activated to acyl-CoA. During this process, two molecules of ATP are used. Now once acyl-CoA is formed, now this acyl-CoA is not permeable to the mitochondrial membrane. So a transporter comes into picture called as carnitin. Now this carnitin is present in the intermembranous space, that is in between the outer membrane and inner membrane of the mitochondria. Now this carnitin will combine with acyl-CoA to form acyl-carnitin. So acyl-carnitin, the job of carnitin is to transport this acyl-CoA. So this acyl-carnitin once formed is translocated into the matrix of the mitochondria by the help of an enzyme called as translocase, or to be specific, what is called as acyl-carnitin translocase, which is present in the inner membrane. Once it reaches the mitochondrial matrix, the carnitin and acyl-CoA will separate out, and it will give, in the presence of an enzyme called as carnitin acyl-CoA transferase 2, which is present in the inner membrane. So carnitin is free. Now this will be pushed back into the intermembranous space by the help of the same enzyme translocase. So this is the second. So this is how fatty acid is transported from the cytosol into the mitochondrial matrix. But remember one point, students, only long chain fatty acid are not permeable through the mitochondrial matrix. So they require transporter, whereas medium and short chain fatty acid can simply diffuse into the mitochondrial matrix. Is that clear? Now, so what is this transporter carnitin? It is basically nothing but beta hydroxy. I said the carbon atom next to the carboxylic group is the alpha carbon, next to that is the beta carbon. So at the beta position there is a OH group, and next to that is the gamma, and the last one is called as the omega carbon. So this carnitin is nothing but beta hydroxy gamma trimethyl. At the gamma position, 3 methyl groups are there, trimethyl, and a nitrogen is there, amino butyrate. So carnitin is nothing but beta hydroxy gamma trimethyl amino. Okay. Now, so what did I tell you? Only long chain fatty acid, that is chain length of 12 to 18, are called as long chain. They require carnitin for the transport into the mitochondria. But I told you medium chain and short chain fatty acid can directly diffuse through the mitochondrial membrane. Now coming to the beta oxidation proper. Now in the mitochondrial matrix you have what is called as acyl-CoA. Now this acyl-CoA, in the presence of an enzyme called as dehydrogenase. Now from the alpha and beta, so this is the alpha carbon, this is the beta carbon, the last one is the omega carbon. I told you all that. Now in between alpha and beta, two hydrogen atoms are removed, and that is taken up by FAD, getting converted to FADH2, and it forms a structure called as alpha beta unsaturated fatty acid, or acyl CoA, or it is called as trans-enoyl CoA. Delta 2, at the delta 2 position there is unsaturation, so delta 2 trans-enoyl CoA, to be specific, alpha beta unsaturated fatty acyl CoA. Okay, now this FADH2 enters the electron transport chain, and then through the electron transport chain it will generate 1.5 ATP. Clear? It will generate 1.5 ATP. Now, once trans-enoyl CoA is formed, water is added, enzyme being hydratase at the alpha and beta position, and it forms a hydroxy group is added, so at the beta carbon or the third carbon, so it is called as beta hydroxy. This is alpha, this is alpha, this is beta. Beta hydroxy acyl CoA. Enzyme is hydratase. What hydratase? Enoyl CoA hydratase. Is that clear? So you have beta hydroxy acyl CoA. Whenever OH and H is attached to the same carbon atom, they are unstable. So immediately hydrogen is removed from these two, creating a keto group at the beta position. So just see here, what happens is a keto group is created at the beta position, and the hydrogen removed is taken up by NAD, getting converted to NADH. So what is removed? Hydrogen. So enzyme is beta hydroxy acyl CoA dehydrogenase. Now this NADH H plus will enter the electron transport chain and give out 2.5 ATP. Okay, is that clear? It will enter the electron. So initially one FADH2 gave you 1.5. Here it is 2.5. Totally 4 ATPs are given here. Now this beta keto acyl CoA removes 2 carbon atoms, okay, from this acyl CoA as acetyl CoA. It forms what is called as acetyl CoA in the presence of CoA, and it gets cleaved, and this enzyme is nothing but thiolase, beta keto acyl CoA thiolase. So now what happens? 2 carbon atoms are removed as acetyl CoA. Now the original fatty acid has 2 carbon atoms less at the end of beta oxidation. So this process will go on continuing till all the carbon atoms of fatty acid are removed as 2 carbon compound, that is acetyl CoA. So we could define beta oxidation as oxidation of beta carbon atom of the fatty acid by removal of 2 carbon atoms at a time. Is that clear? So that is beta oxidation. Okay, is that clear? So it goes on continuing. So what happens to this acetyl CoA? You want energy. That is why oxidation takes place. So it enters the TCA cycle and it will energy. So I repeat once again, acyl CoA is converted to trans-enoyl CoA. Enzyme is dehydrogenase, enters the electron transport chain, and 1.5 ATP is produced. Again hydratase, it forms beta hydroxy acyl CoA. Later, in the presence of dehydrogenase, it is converted to beta keto acyl CoA, and then during this process NADH, which is formed, enters the electron transport chain and generates 2.5 ATP. Is that clear? Now this next, what happens to this beta keto acyl CoA? It undergoes cleavage, that is 2 carbon atom is removed as acetyl CoA. Enzyme is thiolase, so you get acyl CoA. Okay, So this process continues till all the carbon atoms of the fatty acid is removed as acetyl-CoA. Now just the most common fatty acid in our diet is palmitic acid, which is made up of 16 carbon atoms. So how will this undergo beta oxidation? 2 carbon atom is removed, yes, so protein is formed. Again 2 is removed, so it goes on till all are removed as carbon as C2. So how many times the cycle has to run? It has run. So each time 2 carbon atoms are removed. I told you it is made up of 16 carbon atoms. So how many acetyl-CoA you would get? 16 divided by 2, 8 acetyl-CoA. So 1, 2, 3, 4, 5, 6, 7, 8. So how many times to get this 8 carbon atom? The cycle should run 1 is the complete reaction. Now let us see the energetics of beta oxidation. 1 FADH2 and 1 NADH2 are formed per beta oxidation, isn't it so? That when it enters the electron transport chain, you get 4 ATPs, that is 1.5 plus 2.5, that is 4 ATP. Is that clear? So once beta oxidation takes place, 1 NADH2 is formed and 1 FADH2 is formed. So definitely we will have 4 ATP. But for palmitic acid, how many times the cycle runs? It runs, how many times the beta oxidation runs? 7 times. So 7 into 4, right? ATP production also. Initially activation, first step is activation of palmitic acid. We have activated, isn't it so? That time we have converted ATP to AMP. Then how many times the cycle has to run? It has to run 7 times. So how many per beta oxidation, how many ATPs are produced? 4. So 4 into 7 is 28. How many acetyl-CoAs are formed? 8 acetyl-CoA. That will enter the TCA cycle. So for 1 acetyl-CoA, how many once when the TCA cycle runs, it will give you 10. So here you have 8 acetyl-CoA, so you have 80. So 80 plus 28, that is 208 minus 2 for activation. So the energetics of beta oxidation of palmitic acid is 106. Is that clear? So what about beta oxidation of odd chain fatty acid? So when we are talking about even chain. Now odd chain fatty acid, beta oxidation goes on removing 2 carbon at a time till last 3 carbon atom is removed as propionyl-CoA. Okay. Now this propionyl-CoA, so this propionyl-CoA by a series of steps is converted to succinyl-CoA. Once succinyl-CoA is formed, it enters the TCA cycle. Is that clear? This is what happens for odd chain fatty acid. So propionyl-CoA, this we have already seen this under B12. Okay. Remember, when beta oxidation takes place in unsaturated fatty acid, you require 2 more additional enzymes called as enoyl-CoA isomerase and di-enoyl-CoA reductase. In addition to the normal enzymes required, you require 2 additional enzymes called as enoyl-CoA isomerase and di-enoyl-CoA reductase. This much is sufficient. Is that clear? Okay. So let us see how it is regulated. So in well-fed condition, that is when there is enough of fat, what happens? The synthesis of fatty acid is more. So naturally the availability, because malonyl-CoA is an intermediate of fatty acid synthesis. So when melanoid CoA is high, that means that's a well-fed condition. The activity of CAT1, that is carnitine acyl transferase 1, is decreased. So less of fatty acid will enter into the mitochondria, because fatty acid can enter into the mitochondria only in the presence of CAT1 and carnitine. Is that clear? So less fatty acid oxidation takes place. So in well-fed condition, the intermediate of fatty acid synthesis, that malonyl CoA, is increased. That will decrease the activity of CAT1, and that CAT1, if CAT1 activity is decreased, less of fatty acid enters the mitochondria, so there will be decreased fatty acid oxidation. Now in fasting state or high fat diet, what happens in fasting state? The malonyl CoA is less, isn't it so, in fasting state? So what happens to the activity of CAT1? It increases. So more of fatty acid enters into the mitochondria, and there will be increased fatty acid oxidation. Okay. All this time we studied about beta oxidation. Now the oxidation of alpha carbon atom also is possible. What is alpha carbon atom? The carbon atom next to the carboxyl carbon, or the second carbon atom of the fatty acid, is called as alpha oxidation. Now for this alpha oxidation, you require an enzyme called as alpha hydroxylase. So when this is defective, it leads to a disorder called as Refson's disease. So in Refson's disease, alpha oxidation is defective because of the defectiveness in the alpha hydroxylase, which is also called as phytanic acid oxidase. This alpha hydroxylase is also called as phytanic acid oxidase. So phytanic acid is oxidized by alpha oxidation. So when this alpha hydroxylase is not there, what happens to phytanic acid? It is not oxidized, so it gets accumulated in the tissue and plasma. There will be peripheral neuropathy. Both the motor and sensory systems will be affected. Motor weakness is seen, muscular wasting is seen, and there is inflammation of the retina called as retinitis pigmentosa, cerebral ataxia, nerve deafness, and all these are the manifestations. So meat, milk and other dairy products should be avoided because these contain lots of phytanic acid. So what is Refson's disease? Deficiency or defective alpha hydroxylase, or otherwise called as phytanic acid oxidase. So because of this, phytanic acid gets accumulated in the tissue and plasma, resulting in neurological manifestation like peripheral neuropathy, retinitis pigmentosa, cerebral ataxia, nerve deafness, etc. So meat, milk and other dairy products which are rich in phytanic acid should be avoided. Okay, so there will be, so because of this there will be increased level of long chain fatty acid, whereas decreased ether lipids are observed. Okay, this is all you should know about Refson's disease. Thank you.